Hello, I'm Nathaniel Wheaton, and I'm going to be showing you how to model a Eulerian component in Abacus. As you can see here, this is kind of what the results look like. You can see it's compressing, and the pressure is rising, as you can see here. See? So to start, you wanted to define a couple components, at least for this simulation. Um, I ended up using a deformable piston and a deformable tube because when I had previously tried to use rigid components and had gotten issues with the interaction step between them. So as you can see here, I made them all circular revolutions solids. The only thing really special is this air component, which is a 3D Eulerian component. Um, if I go to 2D planar or axisymmetric, you see Eulerian is grayed out because it's not supported for those types of components, which is why I ended up using modeling the full thing instead of being able to exploit the symmetry of the part. Um, okay, for our properties, there's only one really special one. This air component has an equation of state to go with it, and I chose ideal gas, and it put a gas constant of 287 and ambient pressure of atmospheric pressure, which is 101,325 pascals. You also need to add a density and a specific heat because we're going to model it heating up as it's compressed. For the shell, I used a generic steel where I defined the density and all the typical elastic uh, properties of it, like the Young's modulus 200 e to the 9 pascals and a Poisson's ratio of 0.3. For the section assignment, it's nothing particular. When you go to assign the air component, you have to have you can only assign this type of material to this type of model. Like if I click this, you can see there's only air, despite the fact that I have steel also defined in here. And then you just do a typical assignment. See here, I have the part for air pulled up, so it's showing that I assigned Eulerian to it. If I go to deformable and I go to here, you can see I set steel to this component. And it'll be the same for the tube, except I assigned it 3 times because for my assembly, as you can see here, it's kind of an odd thing. If I hide some of these instances, like if I hide the air and I hide the piston slash plunger, you can kind of see in there. The important thing is if I show the air, you can see it goes all the way to the top of the piston, and then if I hide the air again and I show the piston, it's also at the top. So these two, if I select both of them, they're both intersecting with each other. The piston and the air, they're kind of intersecting in this top part. The important thing is Eulerian components stay stationary in space. They only model a mass fraction inside them, which they only model like the flow in and out. They're doing volumetric analysis with integrals over all the sides of the elements. Kind of somewhat similar to a heat transfer problem where you got heat fluxes. You got mass fluxes through these ones. For the step, there's something kind of special here. If I go in here, you see I have a time period of 0.1 seconds. I had wanted to do a 1 second time period, but the simulation time ended up being like 3 hours. I ran it once, and it wasn't particularly better or worse than this short impulse, um, this short motion step. An important thing is Eulerian components. You can't really use mass scaling, because the way that they work, they use the mass fractions. So if you use mass scaling, it makes it way too like stiff slash rigid, which kind of makes it not as useful. Then for my interaction, there's something kind of special here. I have one interaction set up. I have this general explicit interaction. It's an initial condition. Um, and then you have to set all with self for the contact domain. Yeah, you can see that in here. Here's where you assign your frictions and all the stuff. I didn't do that. There's like you just assign friction penalty if you wanted a true 100% realistic simulation of this. For the load, there's something kind of special going on here. So you see, for my piston, I've got it fixed in the, I think for me it's the Z and X position, but it's just in the perpendicular directions to the cylinder, allowing it to move in the Y direction. I've encastrated the bottom of it so it can't move at all. And then if I go to here, you'll see there's a lot of boundary conditions in here, which is just kind of surprising. I've got these two for this one here, for the ones that you can currently see. But then if I go to step 1, you can see there's a whole bunch more in here. There's these 3. This one is a displacement of the top face of the plunger. This one is an Eulerian boundary, which if I edit in here, you can see this is how you model the flow in and out of your volume. So I selected the face that's matching with the cylinder for this, and the bottom one, because no flow would be allowed through those faces. So then I've selected both here, picked my faces that I wanted, select none for both of these. You have to scroll down. It doesn't show initially for the outflow. And then for the top, if you don't set a different one for the top, it'll pull a vacuum. It'll yeah, it'll make a lot of stresses that aren't realistic, because when you push it down, all the air from the environment is actually just going to go right in there, and it's not going to pull a vacuum. So I have free and free as opposed to none. And see, I picked this surface here. You can see it's Z clipping due to them being the same face. For my mesh, I'm using the education edition, so I'm limited to 1,000. With the interactions between Eulerian and Lagrangian, which is the typical solid components that we're used to, it works better, I've seen, if the Lagrangian components are larger components. Ideally, you want the Lagrangian components to be larger than your largest Eulerian component element. That'll help it model these boundaries more correctly. So you can see here I've got these massive tetrahedron elements. This isn't great, but yeah. And for the piston, you can see it's super simple. It's just 4 elements, and that works that's ideal for this type of simulation. If you refined the, if I go to the air, if you made these even smaller, you'd want to maybe make them those ones smaller in tandem, but you could keep them very large. An issue that I run into is I think these large components are prone to leaking um, during the simulation, resulting in some loss as it goes. For something special here that I forgot to mention earlier in the step, um, you want your field output. You want to request a little differently. You see these ones here. This energy and volume fraction, stress. This is the average over the elements, and temperature. And then you want to make sure it's a whole model. I set it to every 0.01. I set it X units of time, 0.01, so I could get a pretty good view of it at the end. But you can do this to your preference. The really important ones are this SV, AVG, and temperature ones, at least for this current simulation. Ooh. Another important thing, if we go to model and edit attributes, or model, edit attributes, model 1, you can see in here, you have to set an absolute 0 since we're going to be doing a thermal analysis, and then you have to set the Boltzmann constant because we're using these gases. You're allowed to set these to whatever you want because Abacus doesn't enforce types or units, so you have to set these to whatever units you're using. I was using meters, newtons, pascals for all of mine, so I use these values, and Kelvin. So if I go to, there's something I also forgot, which was in load. We have these field we're setting some initial fields. We're setting initial temperature. This is roughly 20 Celsius for the temperature of the volume. Then we have we're setting a volume fraction. We're setting it to 1 because we want it to be nice and full of air. And then we're setting our initial pressures/stresses throughout the Eulerian component. I'm setting them to 0 because it's starting at rest. And that's gauge pressure. So it's atmospheric pressure plus the reference pressure that we had earlier. So we have our mesh, then our job. There's nothing particularly special when you set up the job. I had a lot of them because if I show you real quick, if I go to this one, I go to monitor, you can see I did 1 second, and it took 160,000 increments to get this, or a wall time of 764. Well, this isn't a good example. I think it's this one. No, it's not. Here is a good one. It took 2.7 million increments, a wall time of 10,600 seconds, which is about 3 hours. This is why I ended up setting it, like you can see here, 0.1. Well, it's 1. This is why I ended up setting it to 0.1, and, yeah. Another thing. If I go to load, and I go to my boundary condition where I move my displacement boundary condition, you can see here I go negative 0.75, which is like almost to the bottom. But since it's it's a dynamic explicit step, I need to set this. I need to create an amplitude, and I created this one. I just created a smooth step of from 0 to 0.1, 0 to 1. So that at the end of the step, it'll be all the way done. And I'll be all the way at the bottom here. And then I can show you, there's another kind of special thing in here in the visualization. You can see here. Since you can't really exploit symmetry as well as you really want for a Eulerian component, because just generally how it works. Because the thing about it, the mass would be flowing out, and then it would flow in, and if you're blocking that mass, you're going to make some additional stresses in there and velocity barriers, and it's not it doesn't work very well if you exploit symmetry. So I have to set up this section view, which is just the default one since I put it on the axes. The main thing is you have a lot of these values in here. Since it kind of does it for the Eulerian volume and the rest of the part. So like I go EVF voice, like, oh, you can't have that on Lagrangian component. The main one is if you want to get pressure out, you can do this SVAVG, or yeah, and then pressure. That's the important thing. I didn't realize this at first, but you go down to here to pressure. This also works for the directions, all the directional pressures. In this case, they're all exactly the same. You can just add these together and divide them by 3 to get you can add them together, negate them, and divide them by 3 which just gives you this value of pressure. Another one is this temp value. You actually want to make sure you select temp, assembly, air. In my case, it's air 1, air 1. You can see here, it's Z clipping because the plunger is in the component, so there's a little bit of clipping. If you see here, it's like, see? Yeah. Yeah, one of the issues that I found was it's not getting nearly hot enough for it to be completely accurate. It should be getting like, if you use the ideal gas equation, it should be getting like 200 degrees hotter, but it's not, and I think that's just might be because it's like seeping out through the top and going away, like see here. You can kind of see the edges. Another thing that I found interesting was if you measure this velocity, and it's V2, and then I put it actually V1 or maybe V3, V2. You can kind of see it's like pulling it in from the top. Since we set that boundary, that Eulerian boundary condition earlier, you can see it's kind of the air's filling it back in as it goes. And I'll play it so you can really get a good view. Yeah. Okay. Thank you. This was kind of fun.